Hi, this is an example problem from Chapter 25 on concave mirrors. Pause for a moment and read the instructions. So we've been told that we have a concave spherical mirror. We've been given the focal length. We're asked in part A to locate the image and find the magnification for an object. First thing I'm going to do is I'm going to draw a picture of this just so we can kind of wrap our heads around what we're doing. So I'm going to start by drawing the optical axis here. And then I'm going to go ahead and put the mirror on there. So it's a concave mirror, which means the reflecting side is the curved part. So here's our front. It's kind of caved in there, and here's the back. And of course, no light back here. And so we've kind of got this set up now, and we can go ahead now and locate some of the things. So remember that we always measure everything from the edge of the mirror on the principal axis. So if I want to go ahead and do the focal length, let's say right here maybe. Here's F. Well, I guess I should say focal point, capital F. That's the point. The focal length is the distance from here to here. And we know what that's equal to. We've been told that it's equal to 10 centimeters, but we need to check real quick. Let's go look at our sign conventions. Focal length, concave mirror, it's in the front, plus, okay, it's going to be positive. Plus 10 centimeters. Now, I don't need to convert anything in here into meters because the equation that we'll use for the mirrors, it's just all lengths, and so whatever length you use, as long as you're consistent, it's good. Now let's go ahead and put the object. So the object we're going to have to go and measure again from the same spot, and we're going to go out to 25. So here's our object located at this position. The distance of the object, DO, it's in front again, that's going to be positive. We check our sign conventions. Objects with mirrors, again, always positive. Centimeters. And we'll go ahead and draw a little picture here. So we always draw our objects as arrows. And let's see. So part A, we can go ahead and solve this now. Part A, locate the image and find the magnification for an object distance 25 centimeters. Locate the image, that means find DI. So we've got 1 over DI plus 1 over DO equals 1 over F. We're going to try to solve for DI, so let's go ahead and subtract this over. So 1 over F minus 1 over DO. And now we can put our numbers in and we'll calculate 1 over DI. So 1 divided by F, 10 centimeters, positive, minus 1 over DO, 25 centimeters, also positive. This tells us that 1 over DI is equal to 0.06, and this is going to be 1 over centimeters. Now, the common mistake a lot of people forget to do is take the reciprocal here, but we're going to have to take the reciprocal of this to calculate the I, because that's not what we want yet. 1 divided by 0.006 gives us a value of 16.7 centimeters. And I'm going to highlight the fact that this is positive here. So there's our DI. Now to get the magnification here, we're going to use the magnification formula. There's two different ones, but for this one we're going to use M is equal to negative DI over DO. Since we know both of those, let's be a negative 16.7 centimeters divided by 25 centimeters. Centimeters cancel and we get a negative 0.67. So there's our magnification there. Let's look at part B here. So part B, we are asked, determine whether the image, if the object height is 20 centimeters, calculate the image height. We can use our second definition of the magnification now. So the magnification, it's really just a straight ratio. So the height of the image divided by the height of the object. And so here's our object over here. We know that this height for the object is 20 centimeters. And now, knowing the magnification, we can solve this for the height of the image. That's going to be equal to magnification times the height of the object. So we're going to have negative 0.67 multiplied by height of the object, 20 centimeters, which gives us a value of minus 13.3 centimeters. So there's our HI. And in part C, we're going to be asked to characterize this image. Is it real or virtual, inverted or upright, and is it enlarged or diminished in size? Well, we can use, let's go ahead and plot our image real quick. So at the image, we see positive sign here. So that's in front. And we know the position. So I had this at about 20 centimeters. This is going to be at 16. This is 10 here. So we're right around here maybe. This is where our image is going to be. Let's use green for that. And the image, let's see, the sign for the magnification is negative. So this is going to be inverted or upside down. And the height is going to be, it's only 2/3 as tall. Instead of 20, it's going to be 13.3. The negative sign, again, this is the same thing here. This means inverted as well on the height. All right. So if we draw this, we're going to draw something a little bit like this. Right? 2/3 is big, pointed in the opposite direction. There is your image there. So there's our image. All right, so to answer these questions for part C, determine whether image is real or virtual. Well, it is on the front side, and that means that there is actually real light there forming. So the light will actually go from the object, reflect off the mirror, and it'll pass through the image. And so this is going to be real. Now for the next question, is it inverted or upright? Well, we can see it's inverted. And again, we know that because the negative signs on the magnification and the image height. And is it diminished in size or is it bigger? Well, we know that it's diminished because it's not as tall. The magnification here is less than 1, so this is diminished. And again, just to check on whether it's real or not, the front is the real side here. Okay, before we go, let's just double check part C, and we can do that by looking where the object is located. So we've got the object right here. And notice that F is at a position here, and 2 times F is the radius. And so F is 10. The center of the spherical mirror, the radius, in other words, the center of convergence C is here. Notice that the object is outside of C. It's beyond C. Now, if we go and check back with the equation that tells us about mirrors, here's your sign conventions, etc., tells us a little bit about ray tracing. Keep going down. We have a categorization of all the types of images you're going to have based on where the object is placed, right? So for this one, the object, you can see it is outside of C, and the type of image you get is a real inverted diminished image, exactly as we saw, and so that makes sense. Now if you get other placements of the objects, you can always check and see. I know if it's between C and F, you get a certain set of characteristics. If it's inside of F, between F and the mirror, you get a different set of characteristics. And for a convex mirror, you get something else entirely. But you can always check that by looking here on these notes.